So this lesson is about differentiability. So what we've got here is we've got this function f of x, and I'm interested to see if it's possible to find the derivative at x equals a. So the reason why it is okay to find the derivative at x equals a is because, first of all, the point a comma f of a exists. It is on the curve. In other words, the curve is nice and continuous, and I can find a plus h on either side and find these secant lines and make them get closer and closer and closer, and those will agree with each other as to what the pattern is. So to summarize that, what I would say is f of x is differentiable at x equals a if two things occur. First of all, f of x is continuous at x equals a, because I could draw that without lifting my pencil, or I have the limit definition. And also the limit as x approaches a from the left of the f prime of x, and the limit as x approaches a from the right of the f prime of x. Those tangent lines that I was finding, or secant lines I was finding, and the patterns I was looking for coming in from the right or from the left have to be the same. So now notice here there is no f prime of a because I don't know if I can find it. The whole point is it possible to even find f prime of a? So I don't have that in this statement, as opposed to the continuous where I had to add the limit as x approaches a from the left of f of x, the limit of x approaches a from the right of f of x, and f of a all had to agree for continuity. Now, again, differentiable means, is it even possible to find a derivative? Now, the textbook uses slightly different notation, so let me write that for you. So they write it f prime of a from the left and f prime of a from the right. I'm not a big fan of this notation. I would rather write it with limits, so I would prefer that you do that instead, but don't be surprised when you see this notation in the textbook. Now, often this is written a little differently, not using this notation, but instead, of course, this is the continuity part, limit as x approaches a from the left of f of x equals f of a equals limit as x approaches a from the right of f of x. And then they will write this statement about the derivative from the left and the derivative from the right being the same, the limits, this way. The limit as h approaches 0 from the left of f of a plus h minus f of a over h, because that's the first principles or definition of the derivative, and that has to equal the limit as h approaches 0 from the right of, again, the f of a plus h minus f of a over h, again, first principles. So they're talking about now taking points here and getting closer and closer looking for the pattern, taking points here, getting closer and closer and closer looking for the pattern, and making sure that those patterns match up. So these are some scenarios where f of x is not differentiable. I'm not exhausting all the scenarios, but I'm giving you the general principles, and then you can sort of think about it on your own. So the first one is a scenario where f of x is not continuous. I just showed a removable discontinuity, but any discontinuity would work. And the reason this doesn't work is because if you want to do the limit as h approaches 0 of f of a plus h minus f of a all over h, well, you have to have f of a, and there is no f of a here, so you cannot find that limit. So therefore, if the function is not continuous, you can't find a derivative. And this is a scenario where the tangent line is vertical. Now, IB will not actually worry about this scenario, but it is something you should be aware of. The reason why you can't differentiate when the tangent line is vertical is not because you can't find a tangent line, but because that tangent line has no slope. The slope is undefined. Undefined is not a number, therefore you cannot say the derivative at x equals a is this number. So f of x is not differentiable when the tangent line would be vertical. Now this is a scenario where there's a corner, and what's happening is the slopes on one side are giving you one value, if you look at the pattern, and the slopes on the other side are giving you a different value. So at that point itself, you don't know whether to follow these values or these values, and therefore there is no derivative at x equals a, because there is no unique tangent line at x equals a. So here we're asked to show that f of x equals absolute value of x is continuous but not differentiable at x equals 0. So first of all, let me write this f of x piecewise. It's either x if x is greater than or, let's say, equal to 0, or it's negative x if x is less than 0. So first of all, f of x is continuous, so the limit as x approaches 0 from the left of f of x, well, that's the limit as x approaches 0 from the left of this function, negative x, which is going to be negative of something very, very close to 0, so basically 0. Also, the limit as x approaches 0 from the right of f of x is going to be the limit as x approaches 0 from the right of, now that's this function of x, which again is going to be 0. And also, f of 0 is, well, 0 because I plugged it in over here. So these three things say that, therefore, f of x is continuous because they're all the same at x equals 0. Now, differentiability requires continuity, so either way I would have had to do this to check differentiability, but now to show that the function is not differentiable, so now I'm going to do the limit as x approaches 0 from the left of f prime of x. Well, that would be the limit as x approaches 0 from the left. Well, the function is this one. The derivative of negative x is negative 1. Well, that's a constant. The x changing is not going to make any difference, so it's equal to negative 1. And then the limit as x approaches 0 from the right of f prime of x. Well, that's the limit as x approaches 0 from the right of the derivative of this function, which is just 1. And again, 1 is not changing as x goes to 0, so it's just equal to 1. And the fact that the limit as x approaches 0 from the left of f prime of x does not equal the limit as x approaches 0 from the right of f prime of x means that f of x is not differentiable. And we just write diff at x equals 0. Now, if we had found that the function was not continuous, we wouldn't even bothered with this, but of course the thing was to show it was continuous first, but not differentiable. But if the question is it or is it not differentiable, and we found not continuous, we wouldn't even bother. Okay, so find m and n such that g of x is differentiable at x equals 1. Well, first of all, we need to talk about continuity, because without continuity, you can't have differentiability. So continuity means we first need to do the limit as x approaches 1 from the left of g of x. Well, that would be the limit as x approaches 1 from the left of e to the x plus m. And now I basically plug in numbers very, very close to 1, and I get e to the 1 plus m, or just e plus m. And now I do the limit as x approaches 1 from the left, from the right now of g of x, rather. And that's going to be limit as x approaches 1 from the right of the nx minus 2, which again, when I plug in numbers very, very close to 1, becomes n minus 2. Now, finally, I need to do g of 1, because that's a requirement for continuity. But luckily, g of 1 is literally just plugging into here. So it's going to be e to the 1 plus m, or just e plus m. So all three of these things have to be equal for the function to be continuous at x equals 1. But because these two are already identical, it's basically this has to equal this. So e plus m must equal n minus 2. Let's save that as equation 1. Okay, so now I need to talk about differentiability. So once I've got continuity taken care of, I now have to be able to check on the derivative. So the limit as x approaches 1 from the left of g prime of x, well, that would be the limit as x approaches 1 from the left. Well, the derivative here of e to the x plus m is just e to the x. And of course, as I evaluate in year 1, I get e to the 1, or just e. But when I do the limit as x approaches 1 from the right of g prime of x, well, now I'm taking the derivative of this, and it's going to be the limit as x approaches 1 from the right of the derivative of nx plus 2 is just n, and it's not going to change what x is doing, so it's equal to n. And now these two things have to be equal for differentiability, so n must equal e. And now I can substitute back in over here to solve for m. This is equation 2 if you want. So e plus m must equal e minus 2, and therefore m must equal -2. So finally we have n equals e and m equals -2 in order for the function to be differentiable at x equals 1. And that is the end of the lesson.